In this video, we shall prove isomorphism between AV and M. AV is the algebra of all linear transformations and M is the algebra of all n by n matrices over F. So let V be an n-dimensional vector space over a field F. B is a basis of V and M is the algebra of all n by n matrices over F. Now we define this mapping from AV to capital M. This we denote by small m. M stands for matrix. So this is defined by matrix of T, M of T, to be equal to this matrix of T with respect to the basis B. We shall prove that this is a vector space isomorphism, that is M of s plus t is M of s plus M of t for any two linear transformations S and T in AV. That means matrix of s plus t is matrix of s plus matrix of t, and M of alpha t is equal to alpha times M of t. That means matrix of alpha t is same as alpha times matrix of T. We are not writing the basis B here because B is fixed now. And lastly, that we shall prove that M is both 1 1 and on 2, and that will prove that this M is an isomorphism, vector space isomorphism between AV and M. Let B be equal to V1 V2 Vn. We first prove that matrix of S plus T is same as matrix of S plus matrix of T. Now for each I 1 to n, let S of Vi be equal to this vector. S of Vi is again a vector in V, so we can write down as a linear combination of V1 V2 Vn. And suppose similarly T of Vi is equal to this one, beta ij Vj. Let A be this matrix alpha ij and B be this matrix beta ij. Both are n by n matrices. Then matrix of linear transformation S will be the transpose of A and matrix of T will be transpose of B. Now what is S plus T of Vi? This is equal to S of Vi plus T of Vi. S of Vi is this and T of Vi is this. We can combine these two this way. Suppose C is this matrix alpha ij plus beta ij. This is nothing but A plus B, and so matrix of S plus T, which is equal to C transpose, this is equal to A plus B transpose, that is A transpose plus B transpose, and that is matrix of S plus matrix of T. So first thing is proved. Now we prove that matrix of alpha T is equal to alpha times matrix of T. For this you see that alpha T applied on Vi is equal to alpha times T of Vi. T of Vi is this, alpha is outside, this we can take inside here. So we get alpha beta ij times Vj, and so matrix of alpha T will be equal to the transpose of this matrix. We can take alpha outside and the remaining thing is matrix of T. So this proves that matrix of alpha T is equal to alpha times matrix of T. We now prove that M is 1 1 and on 2. First we show that this is 1 1. For this, suppose M of Ms is equal to Mt, then matrix of SB, then matrix of S is equal to matrix of T. Matrix of S is alpha ij transpose and matrix of T is beta ij transpose. This will give us that alpha ij matrix is same as beta ij matrix. Two matrices are equal if their corresponding entries are equal. So this will mean that alpha ij is beta ij for each I and j, and that means that S of Vi is equal to T of Vi for each I, because S of Vi is a combination with alpha ij vectors and T of Vi is a vector with combination beta ij. So if these two are equal, then corresponding coefficients must be equal, and if corresponding coefficients are equal, these two are equal. So S of Vi is T of Vi for each basis vector, and we know that if transformation agree on basis vector, then they agree on all the vectors. So S of V is same as T of V for each V. This shows that S is same as T, and so M is 1 1. Now we prove that M is onto. For this we take a matrix A in M. We shall show a pre-image of this matrix under the mapping small m. Now define T from V to V by T of Vi to be equal to gamma I1 V1, gamma I2 V2, gamma In Vn. Notice that these gamma In, gamma I2, gamma In are coming from here ith column. This is for each I from 1 to n. Then matrix of T will become this matrix A itself, and so M of T will be equal to A, and so M is onto as well. Now in this theorem we shall prove that matrix, that the mapping, same mapping M, when we apply this mapping M on TS, T composition S, this gives us MT times MS. That is, matrix of Ts is same as matrix of T times matrix of S. Now for any I from 1 to n, when we apply Ts on Vi, we get T of S of Vi. This is S of Vi. So this T of this vector becomes summation this Tvj. Now put the value of Tvj. Tvj was this one, beta jk Vk. K varies from 1 to n. This we can write down this way, first with respect to k summation and then with respect to j, and Vk is outside. Now take this matrix as Cik. So we can write Ts of Vi equal to this one, k varies from 1 to n, Cik Vk. So matrix of Ts will be Cik transpose, but Cik is this one, so transpose of this, and this is nothing but the product of the matrices A and B. A is alpha ij and B is beta jk. So this is AB transpose, this is equal to B transpose A transpose, and so this is matrix of T into matrix of S. So with these two theorems we can say that AV is isomorphic to M as algebra. So these two algebra are same up to isomorphism.